Another really good example of wave behaviour comes in the form of sound. The fact that you can hear me now suggests that somehow I'm disturbing the air between me and you. Let's take a look at the physics. So if you remember, sound was a very good example of a longitudinal wave. That when disturbed, the medium would send a pulse, a compression, in the same direction as the wave is moving. The oscillation of my hand on this slinky to make a longitudinal wave is up and down in the same direction as the slinky, just like this. That's why I'm going to pull it up slowly, then I'm going to send the pulse down. And you could see a longitudinal wave went through the medium of the slinky. Of course, with sound, the medium is the air. So here we have a section of the slinky held upright, and we're going to send a pulse along by pulling it backwards and letting it go. But I want to show you what happens in slow motion. So if I was to represent that longitudinal wave on this board, then maybe I could draw positions of that spring. Now I'm going to draw it, and obviously it would be like a coil with a piece going behind to join back up and then round again and then round again. But I'm going to try to draw it like this. Now, undisturbed, the slinky has equal spacings between each of the individual spools on the coil. But then what happens, and what we saw on that slow motion video, was that when the wave passed through, it caused a compression. The space in between those spools got smaller. And then, at other times, immediately before and after the compression, the actual spring was slightly more extended than it normally is. And that makes sense. It can't be compressed here unless it's getting some spring from somewhere else. And so what happens is you get a pattern that looks kind of like this. I'm drawing it as carefully as I can so that it is clear for you. And as you can see, I've got another compression here, and then I'm going to start widening it out again. Now in reality it should be the same height all along. It's a diagram of the spring. And so this here, this point here, this is a compression. And this bit here in the middle where it is spaced apart is called a rarefaction. Some people struggle with this word. What on earth has rare got to do with being spread out? Well, we might describe the air at the top of Everest as being rarefied, being very thin, very extended. And the air in here is rarefied because if this was sound moving through the air, then it's not physical compression of springs. It's the particles of the air being forced closer together, like the spring, and the particles of air being more spaced out in the rarefaction. Now, on a diagram like this, what is one wavelength? Well, one wavelength is equal to the distance between one compression and the next. That is a wavelength. As different to light, where we describe it in terms of wavelength all the time, and that's a historical reason, because the very first thing that we knew about light was its wavelength, and we could only infer its frequency after we discovered the speed of light. But with sound, the first thing that was more obvious to us was the frequency, and only by measuring the speed of sound were we then able to infer what the wavelength was. So from this point onwards, we will always refer to sounds with frequencies. So check this out. This is a signal generator, and this is an old-fashioned speaker. And what I can do is I can make sounds come from this as produced by the speaker. Turn it on. And you can now hear it's making a very low noise indeed. Now what I'm going to do is I'm going to take the camera really close in to this so that you can see what it is doing. So the cone of the speaker gets to push forward and pulled back, and you can see at this very, very low note the actual motion occurring. Now that motion is still slightly too much, so I'm going to turn the frequency down, and what you should notice is the motion becomes more readily visible. And if I take it all the way down, you can now see the speaker vibrating in and out, and that is what a speaker is doing when it produces any sound. It is just shoving the air in front of it backwards and forwards. This shoving effect of the air is what causes the first compression that moves through the air itself. Your larynx, your voice box, compresses the air in the same way. This is how all sound systems work.